Welcome to part 2 of these lecture slides on decision diagrams and the ADLib framework. In this lecture we will talk about ROBDDs, or reduced ordered binary decision diagrams. So, what are the basics of a reduced ordered binary decision diagram? When people talk about binary decision diagrams today, they're generally talking about ROBDDs. These are binary decision diagrams that are optimized. Again, they have fixed variable ordering and have a canonical representation, so a single minimized representation that no matter how many people you give it to, you're only going to get one single return. To construct a reduced order binary decision diagram, there are three main steps. First step is to remove duplicate terminal nodes. Second step is to merge isomorphic decision nodes. Third step is to eliminate redundant tests. Before we go through these three steps, we will first look at the example we are trying to construct. And let's move on to our example. So this is an email example. So we get a scenario. Email is classified as urgent if the subject contains urgent or deadline and is from the government. It is also classified as urgent if an email contains none of the above properties. So before we go through this, let's start in the box on the right hand side. So our function in this is email urgent. So that's just the name of what I'm calling this scenario. So this would be the function you would have at the top, going down to your clauses. A function contains a clause, an operator connecting, and second clause connecting a third clause, an operator to a fourth clause, etc. So that's what a function is. And these are Boolean operators, so and, or are generally the two connectives. A clause is a predicate, an operator, or a predicate. Now why is this in red and this in blue? This operator represents this or here, so this joins clauses together. This operator joins predicates together, so this is represented by the blue here. So clauses are generally within the brackets, and the operators joining our clauses are outside the brackets. So we are representing here a DNF function, or a disjunctive normal form, which essentially is clauses connected together through OR operator. You could just as easily have OR clauses connected by AND operators, which would be conjunctive normal form, or CNF. So our operators again are AND, OR, and NOT. Our predicates in this case, so let's go through our example. Email is classified as urgent if the subject contains urgent or deadline. So we can put brackets around that and go, this is a clause, because we found an operator, or. And is from government, so we found another operator, and is from government. Predicates are urgent, deadline, and from government. So we mark these down here. Subject contains urgent, it's from the government, and subject contains deadline. Also classified as urgent if an email contains none of the above properties. So this again would be our not operator. So it's not contains urgent, and not from government, and not subject contains deadline. Finally, our terminals are true and false. So let's look at our function. Email urgent, which is our function name, equals opening bracket, and then we have our closing brackets down here, so it's everything in between these two brackets. Subject contains urgent and from government, or from government and subject contains deadline. Now you may be wondering, why was it done like that? if you look at this representation, x1 or x2 and x3, this is equivalent to x1 and x3 or x2 and x3. So we have changed our initial formula into D and F. So AND clauses connected by OR operators, which is what we were trying to do. So that's essentially what we've done in the start. Here with subject contains urgent and from gov, or from gov and subject contains deadline. And finally, our final clause is or to not subject contains urgent and not from government and not subject contains deadline. And now we have our final function with our three clauses. We can now begin the construction of our binary decision diagram. Any ordering of the variables can be selected but must be maintained afterwards. So again, we have 2 to the power n minus 1 decision nodes, so we're going to have 7 decision nodes. So again, we had our function, which is our root, which is email urgent, goes down to subject contains urgent, and again, as we saw earlier with the decision tree, you have your true, false, go down to the from gov, again we have our true, false, and then we go down true, false, false, true, false, false, true, true. So this is the same as the function we had before. So step 1 of our reduction process is to remove duplicate terminal nodes. So this involves remove repeated terminal node values and redirect incoming edges to remaining terminals of same value. So what does this mean? So as you can see from our binary decision tree, we have a true, false, another true, false, false, true, true. You can see that we have 1, 2, 3, 4 true terminal nodes. And we also have 1, 2, 3, 4 false nodes. So we can transform this into a single false node and a single true node. And now we have to redirect the edges that are coming in to all, let's say, our true terminal nodes and redirect them all onto our now single true terminal node, and also do the same procedure for false. So we had 4 lines coming in, and now we have 4 lines coming in to the single false terminal node and single true terminal node. That is all step 1. Step 2 is to merge isomorphic decision nodes. So what is an isomorphic decision node? This is when 2 of the same parent variable nodes have the exact same high and low pointers. This means that each parent's high pointer goes to the exact same child node, and each parent's low pointer goes to the exact same child node. The word exact here is very important because it must be the exact same child node. So child nodes may have the same name but be different, aka they have different parents. Child nodes can be decision or terminal nodes. So what you do when you have isomorphic decision nodes is you merge parent variable nodes and redirect the incoming edges. Note, there was no such scenario occurring in our decision diagram, so I just made an example of merging procedure below. You can see here the from gov predicate. Low pointer goes to subject contains deadline, and from gov on the right also low pointer goes to subject contains deadline, and also both their true pointers go to subject. This subject contains deadline. So this can then be joined 2 from govs into 1 from gov, redirect the incoming edges, and then you have 1 low pointer and 1 high pointer going to subject contains deadline. Let's go through this in more detail. So what do we mean by isomorphic? Let's take a look at this example. So here we have x1, x2, and x3. We use these variables instead of email urgent, from gov, or contains, newsletter, etc. So x1's high pointer goes to x2, x1's low pointer goes to x2, that is fine. Now we'll take on the left x2. High pointer goes down to x3, and low pointer goes down to x3. Also on the right, we also have x2, whose high pointer also goes to x3, and low pointer goes to x3. However, this is not isomorphic. These are because these children on the left are not the same children as two on the right. Even though they're all named x3, the two on the left, their parent is x2, underlined in blue. The two x3s on the right, parent is underlined in green. So they all have different parents. Therefore, they're not isomorphic. What we mean by isomorphic is, as you can see in this example, now x2 on the left, high pointer goes down to this x3, low pointer goes to this x3. On the right, x2 once more, high pointer goes to the same x3 as one on the left, and low pointer goes to the same x3 as on the left. Now, these are isomorphic. Both low pointers go to the same child, both high pointers go to the same child, and they're both x2 parents. This means we can now join these two x2s together, or merge them. So now we have our final decision diagram. So notice we now only have one single x2 parameter, with a then going to x3 and the else going to x3. And two edges have now been, the incoming edges have now been redirected to the single x2 predicate. So this is what we mean by merging isomorphic decision nodes. 3, we want to eliminate redundant tests. So remove unneeded nodes. The edges of a child node both direct to the same decision node. We want to remove the redundant child node and connect edges directly to the decision/terminal node. So if you see in our example below, email urgent goes down to subject contains urgent. Now in the false, it's a subject contains urgent is false. You go down to from government, subject contains deadline, and then if it's false, it goes to true. If it's true, it goes to false. And in this subject contains deadline, false goes to true, true goes to true in this case. But let's go down the true value side here. So subject contains orange is true. Go down to from government. If from government is false, it goes on to subject contains deadline. Now, if subject contains deadline is false, it points to the false terminal. If it is true, it also points to the false terminal. So, do we really need this subject contains deadline predicate? Because if government is false, from gov is false, it's always going to go to false. The same with the subject contains deadline and the true or the high pointer from gov. From this predicate, if it is true, it goes to true. If it is false, it also goes to true. So again, we don't need this predicate either. Because if from gov is true and contains urgent is true, it's always going to be true. So this brings us over to the diagram on the right, where we can remove both these predicates. And now when subject contains urgent is true, goes to from gov. And if from gov is false, you get false. And if it's true, you get true. So we removed unneeded nodes. You can see a reduced ordered binary decision diagram. We've gone from what we had at the start, we had 7 decision nodes and 8 terminal nodes. We now have 5 decision nodes and 2 terminal nodes. You can see how that saves, first of all, in memory, from 15 nodes down to 7, and also in time, because we no longer have these 2 decision nodes that were here, that were in these positions. So if subject contains origin is true and from gov is true, we automatically go straight down to the true terminal node. So we save in time on the true side. And that is the process of reducing binary decision diagrams. Boolean decision diagrams can then be joined together or composed into a final decision diagram and used as an overall classifier. So essentially we have our function here, email urgent, and this is using 1, 2, 3, 4 decision diagrams. In the composition, we can use our Boolean connectives and, or, and not. And our valid operations between the Boolean decision diagrams, again, is and, or, not, NAND, NOR, XOR, etc. In this example, we are connected to the root using an AND connective. It could easily also be an OR connective, or in rare cases, a NOT connective. Connected to this is not AND or NAND. Subject indicates urgency and trusted sender. And on the right hand side we have an OR. Subject contains deadline from shops. Subject indicates newsletters. So it's NAND and OR, also known as exclusive OR. And OR. I know not exactly because we're using different predicates on either side, but very, very similar. So that's just to show how you can combine them into one single composition. And what you have to be careful when joining Boolean decision diagrams is to ensure graph reachability. If you were to add in another decision diagram here, you do not want to add it on, let's say, here. Let's say OR, going to here, going to here, as that would not be reachable from this Boolean function here. What you want to do is generally have 2 decision diagrams per connective, as seen here. What you want to do, if you want to add in more, you want to join off this operator. The function root can reach. So what you want to do is you add in your next OR here, and then you can add in more Boolean decision diagrams as you see fit. Then this will generate code automatically that can be used to classify incoming data. That is all for this lecture. In our next lecture we will focus more on the ad lib framework. Thank you very much.